Alright, so this is our next video for Math 1560, Calculus 1 at U of L for fall 2017. So the previous videos were in section 4.4 looking at linear approximations. Now we're going to move on to section 4.5 and we're going to consider polynomial approximations. Okay, so we know what the linear approximation looks like. Let me switch to tablet mode, a bit better. The linear approximation for our function is essentially given by the tangent line, right? It's the tangent line approximation. So remember that if we take y here and we set it equal to L of x, that gives us the equation of the tangent line to the graph of f at the point x equals a. Right? So this gives us the tangent line, and it gives us an approximation to the value of our function. But we know that this approximation only really works if we stick close to this point A, right? So the quality of the approximation, the kind of, we want to make sure the error is not too big, so we can make that error small as long as we keep the difference between x and a sufficiently small. So as long as x minus a doesn't get too big, our error doesn't get too big, we have a good approximation, right? And we can see that if we look at any graph. Okay, so here's the graph of some polynomial function, right? So we went with this cubic function here. Okay, f of x is x cubed over 10 minus x squared over 2 plus 2. Those coefficients are just in there to make sure that my scale doesn't get too outrageous. And I've drawn the tangent line at one particular point. Okay, a equals negative 0.45. And so we can see that, as long as we don't move too far away from that point, well, then our approximation is pretty good. And we could adjust that point a little bit if we wanted to. We could move things over, let's say, to maybe minus 0.5, or we could go maybe over to 0. And we say, oh yeah, that seems pretty good. That's a good approximation, but it's only a good approximation if we stay close to 0, right? I would not want to use that to approximate the value of my function at 2 or at 3. Certainly not, let's say, when x is equal to 7, right, where the graph is heading way off. Then my error is huge, right? But as long as I don't move too far away from that point, right, when I look at that tangent line approximation, if I zoom in on that point, we can see that there's not a lot of distance between the tangent line and the curve, right? So even moving out by point 1, by point 2, by point 3, it's not too bad, right? So we're at 0.45, and even if I go all the way out to say 1, right? So my delta x here is a little bit bigger than 0.5, right? My delta y is still only 0.1. It's pretty small. That's probably in a lot of situations that's an acceptable error, right? We go all the way back to 0, we can still see we got a delta y that's less than 0.1. So we're pretty happy about that. Now, something else that you notice if you start looking at these is that the error depends on a couple of things. It depends on how far away we move from that point, but it also depends on where we are on the graph. If I were to move my point over to say around about there, okay, so what I'm doing here is I'm moving over until I get close to the inflection point for my graph, right? So somewhere around 1.5, between 1.5 and 2, there's an inflection point in this graph. It changes from concave down to concave up, and so here we can see that my approximation is pretty good over a pretty wide range of values, right? All the way from maybe 0.5 up to 3. I've got a decent approximation. So what's the difference between those points? What's the difference between doing the approximation near this inflection point compared to, let's say, doing the approximation near maybe that local max or down here at that local min? Well, the difference is the concavity, the curvature of the graph, right? At that inflection point, the second derivative is really small, right? At the inflection point, the second derivative, in fact, is tiny. And so we know that the sort of deviation, let's call it the deviation from being linear, is measured by, well, roughly speaking, by concavity, right? So, in other words, by the second derivative. It might be that, you know, if you're dealing with some higher degree polynomial or more complicated function, maybe the second derivative also, you know, vanishes, and the effects depend on higher derivatives, third, fourth, fifth derivatives. But roughly speaking, this is going to depend on that second derivative, right? This deviation from linearity. And so the smaller f double prime is, the better my approximation is going to be, because if f double prime is close to linear, well, then my function is close to being linear near that point, right? And as we move, well, you know, the values of my derivatives change, the curvature changes, and so the quality of my approximation changes as I move around. And just to give you an idea well, actually, let's move forward, and then we'll talk about that in a bit. So we want to say, well, okay, how can we account for this second derivative, right? Well, we can't do it with a linear function. If we want to account for second derivative effects, we've got to move on. We've got to consider higher degree polynomials. So we want to move to, let's say, a quadratic function, right? So let's say we're looking for now a degree 2 polynomial to approximate our function. You'll notice that I've written my polynomial in terms of powers not of x, but of x minus a. And there's two reasons for doing that. One is simply for comparison with the linear approximation, where we see that x minus a showing up. The other reason is that this makes it really convenient when we want to evaluate at x equals a, right? So we want to, you know, if we want this quadratic polynomial to kind of match up with whatever function we're studying, well, obviously they need to agree at the point where you're making the approximation, and you want the first derivatives to match as well. Notice that this condition here is satisfied by the linearization, right? L prime of x is equal to f prime of a everywhere, so in particular it's equal to f prime of a when x equals a. And then you want to move on and require, okay, not only should the functions agree at the point and the first derivatives agree at the point, you want the second derivatives to agree at the point as well. So we start looking at, okay, what do we have here? So here's where these powers of x minus a come in handy, because if I want to calculate q of a, well, then x minus a is 0. So the higher order terms disappear, and I simply have this constant term, a0. We want that to be f of a. What do we get for the first derivative? Well, the derivative of my constant goes away. I get a1 times the derivative of x minus a, which is just 1. And then I get 2 times a2 times x minus a when I take that derivative. So that means that q prime at a, and again the x minus a goes away because a minus a is 0, and I simply get a1, and I want that to be f prime of a. If I go on and I calculate the second derivative, well, the constant goes away. I just get 2 times a2 times the derivative of x, which is 1. So I get 2a2. And that is certainly, that's a constant, so that's definitely going to be my value when x equals a. So 2a2, and I want that to equal f double prime of a, and that tells me that a2 should be f double prime of a divided by 2. So I get this value here for my a2, here's my a1, here's my a0. And so that means I get a polynomial that looks like this. Q of x is going to look like f of a plus f prime of a times x minus a. And if we stop there, we've got the linear approximation, but we're going to add one more term. We're going to add a f double prime of a over 2 times x minus a squared. And that's my quadratic approximation. So to see what that does for us, let's come back to this graph that we had. Okay, so here's my linear approximation. Let's move back to a point where maybe the linear approximation is not ideal, right? It gives me a good approximation if I'm close to the point of tangency, but as soon as I start moving away, that linear approximation kind of falls apart on me. So let's throw in the quadratic approximation. Here it is. Maybe let's make it a different color so we can see it a bit better. Let's make it red. Okay, there's my quadratic approximation. So now we can see that q of x, the agreement between q of x and f of x, is better, and it's better over a wider range of values, right? I would accept this approximation maybe all the way from -1 up to maybe 0.5. I'd say that's a pretty good approximation there, right? It's still going to fail if I get further away, right? If I move out to say 2.53, we can see that the approximation is way off. On the other hand, going to negative values, we can see that the two track each other pretty well. And again, we can look at what happens if we start moving this point, right? If we move a over, we can see that we get a really good approximation near the minimum. And we can move along, and we can see that, okay, there, both functions seem to do pretty well, and you can kind of play with this, and you can see that, yeah, near that inflection point, they're both doing pretty good again, right? And so you can continue along, and you can see how things change. You can watch both the linear and the quadratic approximations and see how they do. Again, as we get close to that minimum, we see that the quadratic approximation does quite well. We don't quite hit that minimum. It's somewhere in between 3.3 and 3.35. But so that quadratic approximation is doing a pretty good job for us. Okay, and now once you've got a handle on this, you might reasonably guess that if you continue this process, you can get better and better approximations if you continue to add higher order terms, right? Now that one that we had on the graph, it's a cubic polynomial, so if we add one more term, we're going to get the function. We're going to have it exactly, and so then of course, well, you can't do much better than that. But in general, you can try to improve on this. You can move to a polynomial approximation. So you can add the constant term, you can add the linear term, which gives you the linear approximation, quadratic approximation, and then you go on to cubic and higher terms. And again, if we want to approximate our function, so to approximate f of x, what do we require? Well, we're going to require that p of a has to equal f of a, and that tells me that a0 has to be f of a. I'm going to need p prime of a to equal f prime of a, and we know, because we've seen that already, that means a1 is going to have to be f prime of a, because when we calculate p prime of x, we get a1 plus 2a2 times x minus a plus 3a3 x minus a squared, and so on. Right. So when we move to the second derivative, we want p double prime to equal f double prime, and when we calculate p double prime of a, so p double prime of x, we get 2a2 plus 3 times 2 times a3 times x minus a. The next one on the list would be 4 times 3 times a4 x minus a squared, and so on. And so we see that A2, we need A2 to be f double prime of a. So 2A2, so p double prime of a is 2A2. We want that to equal f double prime. So to solve for A2, we divide by 2. A2 has to be f double prime of a over 2. And you continue this process. So if we move to the third derivative, we want the third derivatives to agree. And if we calculate p triple prime, we find that we get 3 times 2 times 1 times A3 is the constant now, and then the next term is going to be 4 times 3 times 2 times x minus a, plus other stuff that depends still on x minus a. So when we put x equal to a, all those other terms go away, and we're just left with this one. And we want that to equal f triple prime. So to solve for A3, we get f triple prime of a over 3 times 2 times 1. And if you continue, you find that if you kind of continue with this pattern, you find that A4 is going to be the fourth derivative at a over 4 times 3 times 2 times 1. And in general, the nth term is going to be the nth derivative at a, n minus 1 down to 2 and 1. Okay, so we multiply those numbers together. That's how you set up this polynomial approximation, right? So you calculate derivatives to determine these coefficients, and you use those coefficients to determine your polynomial. And we can clean up this notation a little bit if you've probably encountered this symbol before. Okay, factorial notation. Okay. The symbol k with this exclamation mark, you read this as k factorial, represents the product 1 times 2 times 3 all the way up to k. So it's the product of the first k integers. So then this, oops, I don't know why that moved on me. So this term here becomes this is the third derivative over 3 factorial. 2 times 1 is still 2, so that's a 2 factorial, right? This is 4 factorial. This is n factorial. So you can write them all out using this factorial notation. So we'll finish with a quick example. Let's say we want to calculate a degree 4 approximation for this function f of x. Okay, so we've got to start calculating derivatives. So f of x is x to the 1/2. F prime of x, 1/2, x to the minus 1/2. F double prime of x is going to be minus 1/4, x to the minus 3/2. The third derivative is going to be 3 over 8, x to the minus 5/2. I did 1/4 times the minus 3 over 2 to get there. I need one more derivative. The fourth derivative, I go 3 over 8, I multiply by minus 5 over 2, that gives me minus, so 3 times 5 is 15, 8 times 2 is 16, x to the minus 7 over 2. Okay, so my A0 is f of 1, which is 1. A1 is f prime of 1, which is 1/2. A2 is f double prime of 1 over 2, which is going to be 1/2 times minus 1/4, which is minus 1 over 8. A3 is going to be the third derivative at 1 over 3 factorial. So 3 factorial, that's 1 times 2 times 3. That's 6 times So the third derivative at 1 is going to be 3 over 8. So I can cancel the 3 and the 6 there. Leaves me with 1/2 times 8. I get 1 over 16. And a 4, I get the fourth derivative at 1 over 4 factorial. So 4 factorial is 1 times 2 times 3, which gives me that 6, and then times 4. So 1 over 24 times minus 15 over 16. And that's going to be, let's see, so I can cancel the 3. 15 over 24 gives me 5 over 8. So I get minus 5 over 8 times 16. So 8 times 8 times 2. 5 over 128. And so that gives me my polynomial, my degree 4 polynomial, approximating my square root function near a equals 1 is going to be 1 plus 1/2 times x minus 1 minus 1/8 times x minus 1 squared plus 1 over 16 times x minus 1 cubed minus 5 over 128 times x minus 1 to the 4th. So we'll leave it at that because this video is already running on a bit. One of the things you might want to try from here is plot this polynomial and plot the square root function on some graphing utility and see how well they match up. So in the next videos we will formally define the objects that we're working with here, and we'll do some more examples.